Okay, so we're going to pick up here chapter 14. As I believe we finished chapter 13 the other day. All right, so chapter 14, this is exam 2 material, officially the big chapter, one of the two big chapters of the season here. The one people really struggle with, this one and the next one, which is 14 and 15. So in this chapter, we're going to talk about acid-base equilibrium. Which means we're basically going to talk about buffers and we're going to talk about titrations in this sort of chapter, and we're going to talk about all kinds of things about both of those things. And again, this is really, as I mentioned several times throughout the semester so far, this is really where the conceptual understanding and the math does need to kind of come together so that you do sort of the correct calculations along the way. The good news is, as we will see, a lot of the calculations we've sort of done already. It's just you have to know when to apply them correctly. So we'll get started here with the idea of the common ion effect. And the idea of a common ion effect is that when we have an equilibrium and we have a presence of a common ion there, it will cause a shift in the equilibrium. And it will really suppress the ionization of a weak acid or a weak base. It basically will keep it from coming apart, and it will kind of keep it together. And if we take, for example, a weak acid like our friend acetic acid here, and acetic acid, which is a weak acid by itself in a beaker, will basically break apart a little bit here. It is a weak electrolyte, so we'll produce some acetate and a little bit of H plus ions in that particular solution. Now, when we have a presence of, say, acetic acid and something like sodium acetate, which is like a salt, it will actually cause some shifting to occur here in this equilibrium. So if we have something like sodium acetate, which is a salt, which means when it goes for a swim, it is not going to set up an equilibrium. It is basically just going to produce ions like sodium ions and acetate ions. Yep. And when we have, say, our acetic acid there in the beaker, and we add some sodium acetate to this beaker, we already have sort of this set up there in the beaker. We could have an equation. So we're basically going to toss this in, and it's going to be a source really of these two ions. And when it goes in for a swim here, we could hopefully see that it is actually the acetate ion, right? Is our common ion in this particular case. We have the acetate ion here, and this is going to be our common ion. Now, essentially what we're doing when we add the sodium acetate to this beaker is we're really increasing the amount here of acetate that was in that solution to begin with. Our friend Le Chatelier would say that the equilibrium then should shift which way? It should shift to the left, away from where we're adding it. So with the presence of this additional amount of this common ion that's in this equilibrium that's been set up, Le Chatelier's principle is going to tell us it's going to shift back this way. Now, when we think about that as being an acid, that's kind of important because that's going to basically keep our acid together, which means it's not going to be able to act as good as an acid as if the acetate wasn't there. That's going to mean in terms of the pH. Would we expect the pH to be higher or lower than just acetic acid by itself? What do we need when we calculate pH? pH is minus the log of. Right. So if we have acetate in this beaker here and we have our equilibrium shifting to the left, that means will we have more or less H plus free in the solution? Less. Yeah, that's going to go down, which means the pH will actually go up. Not maybe basic up, but it will be higher probably than if you had acetic acid in there by itself, because what's going to happen with that extra acetate coming from the sodium acetate, it is going to cause that equilibrium to shift to the left, and we're going to have less free H plus in that solution. And it's the amount of free H plus in that solution that basically determines the pH of that solution. So less H plus free in the solution, we'll actually see a higher, still acidic pH than what we would see with acetic acid by itself. So this is the effect of a common ion. And in most cases, our common ion is going to be on our product side. So it's like Le Chatelier's principle. It's basically going to send it the opposite way, and it's going to keep that weak acid together more than it would if it wasn't present. The same sort of effect would happen in a weak base situation. It would keep the weak base together, which means it wouldn't be able to react with water all that much and produce less OH minus, and it would not act as strong as a base. And you would actually end up the opposite effect in that case. You would have a lower pH because you would have less free OH minus in that solution because of the presence of the common ion. Question on that there. So let's see how we will deal with these problems here. We'll start with part A first. We want to calculate the pH of a solution of 0.2 molar acetic acid. Ka value of acetic acid 1.8 times 10 to the minus 5. So for time being, just work on part A, which should be like review for Tuesday. So let's take a look at the first part here. So first part, we want pH of an acetic acid solution that is 0.2 molar. We have a Ka value for acetic acid. So once again, that definitely tells us it's a weak acid, which should automatically signal you to do an ice table, right? So those are things you want to think about. This is basically just a basic Ka type problem like we did in the previous chapter here. So we'll do it here, which is part A. 0.2 molar acetic acid, and our Ka value 1.8 times 10 to the minus 5. So because it's just a Ka type problem, we're going to start with our acid dissociating here. Going to drop off an H plus to the other side here. And we will get acetate that's left over. Initially, we have 0.2 of our acetic acid. We got nothing here on our product side. Change will be minus x plus x plus x in this case. That means at equilibrium, we got 0.2 minus x, x, and x. Any questions on the ice table here so far? Like normal, we're going to take our equilibrium line and we're going to put it into our Ka expression in this case. And our Ka value is going to be the concentration of H plus times the concentration of our acetate, which is our products, divided by our reactants, which is our acetic acid. And once again, that's going to equal 1.8 times 10 to the minus 5. Popping those guys in there is going to give us x squared over 0.2 minus x. This is a small value of K, so why not try the assumption here? So I'm going to assume that X is equal to 0. Once again, in this case, it's pretty much just that X there that we're going to get rid of. That will leave us X squared divided by 0.2 equals 1.8 times 10 to the minus 5. Once again, we're going to multiply to the other side and then come back and do a little square root action after that. And we're going to go 0.2 times 1.8 to the minus 5 and then square root it. And that's going to give us, I think, an x value here of 0.001897, we'll call it. Remember, we do need to check our assumptions. So we're going to take this and divide it by 0.2 times it by 100 to check it. And if we do that there, I think we're fairly good. We're like a 0.9%, which is good, right? So our assumption here is going to be good. Once again, that does mean in case of the pH, we're really just interested in the H plus concentration at equilibrium. And we can see that it equals X. So that would be basically our H plus concentration. And now we have really everything we need to go into our pH. So our pH will be minus the log of the H plus, and that's going to give us minus the log of 0.001897, and that will get us a pH of something. 2.27 looks like a winner there. Any questions on that one? So that basically is just a Ka problem like we did in the previous chapter. This is just a weak acid by itself. Any questions? So now let's take a look at part B here together and see what happens to the same acetic acid solution if we take the acetic acid solution, and in addition to having the acetic acid solution there, we're going to throw in there 0.3 molar sodium acetate with it. So we're going to drop in there here a salt with our weak acid. So this is going to be part B, which we have 0.2 molar acetic acid. And again, here it was 0.3 molar, I believe, sodium acetate. And we still have the same Ka value there of 1.8 times 10 to the minus 5. All right, so we got a couple of things going for a swim here. We definitely know our weak acid here is going to set up an equilibrium. As we talked about a second ago, this, though, is a salt, which means it is not going to set up an equilibrium, right? It's just going to break apart in solution. So this guy's just going to completely break apart into a sodium ion and an acetate ion, yeah. And that means that the only place where we could do an equilibrium type setup is going to be our acetic acid. So that is where we want to start with our ice table here, and we'll have a little H plus and acetate happening. So initially here, we do have 0.2 molar here of our acetic acid. We have none of the H plus. Now, what about the acetate? Do I have any acetate? I do initially because I dumped in there some sodium acetate, right? So by dumping this into the beaker with this guy, it produced some acetate, and that acetate is our common ion here. So the difference here in the ice table, when you have this common ion present, is you need to have an initial concentration here on our product side. In this case, it would be 0.3 molar, as this is a 1-to-1 relationship between those two, which means the concentration of this guy would also be 0.3 molar. So this is, I would say, 99% of the time where people screw up when they do this type of ice table in this situation is they just zero out the right-hand side. If I zeroed out the right-hand side, what type of problem am I doing? The exact same problem I did in part A, which is just a weak acid problem. So it's not a common ion problem. So it's really important that you have that initial concentration on the right-hand side. Otherwise, you're just kind of repeating the same calculation we just did. Any questions on that there? Now, the rest of the ice table here is pretty much going to be the same. We're going to have our minus X, we're going to have our plus X, and our plus X, which means when we reach equilibrium, we got a 0.2 minus X and X. And this is also maybe the second place where people screw up on this table. It is 0.3 plus X, not minus X. So again, it's plus X on that side. Just like normal, we're going to go into our Ka expression, since this is the only thing setting up an equilibrium in this sort of mixture. And it's still going to equal the same Ka value that we had for acetic acid, because once again, that is the only thing in the setup there. So we're going to have here essentially X times 0.3 plus X divided by 0.2 minus X. And again, that's going to equal our 1.8 times 10 to the minus 5. So since the assumption worked okay in the first place, why not try it again here? So I'm going to again assume that X is equal to 0 in this case. Now, in this case, though, we do get to knock out a couple of X's. We're going to get rid of this X and this X, anything we're adding or subtracting something from. And that's going to reduce this down to maybe something that's a little bit more manageable. X times 0.3 divided by 0.2 equals 1.8 times 10 to the minus 5. In this case, we're going to multiply by the 0.2 and then come back and divide by the 0.3 in this case. And that's going to get us maybe a calculator, 1.8 to the minus 5 times 0.2 divided by 0.3. And that is going to give us here a X value. I won't write all the zeros. 1.2 times 10 to the minus 5 in this case. We still should check it. Probably going to be okay. So I'll just divide it by 0.3 and times it by 100% to give it a little check. And we are even times 1,000 by mistyping it. Nowhere even near like 0.1%. So the check here is good in this case, right? So once again here, we're interested in the H plus concentration. You're going to go back to our table, and just like in the previous one, we can see that X does equal the question. Yeah. You can actually divide by either one. So if it works for one, it should work for the other. So you could check them both. But usually if one's good, the other one would be good. So you could check either one. I took that, or you could take the smaller one, which might give us again. We're still way good at 6 times 10 to the minus 3%. So it's either way you can check. So, but you should at least check one for sure. Yeah. Other questions? All right. So that X does equal our H plus concentration. And that means it's 1.2 times 10 to the minus 5 molar. That means that's all we need for our pH. So I'll go up here so it might be easier to see. pH equals minus the log of 1.2 times 10 to the minus 5. And that is going to get us there. If I punch the right numbers in, might be helpful. There we go. We'll go with a 4.92 in this case. First off, any questions on the calculation? So we could still use an ice table, kind of like just like a Ka type problem, but this is what I'm talking about in this chapter for sure. It's just these little things that you have to watch out for, like making sure you have a concentration on the right-hand side. Otherwise, you just kind of wasted your calculation. You're going to get the wrong answer. So very important, the little things in this couple of chapters that we're talking about to make sure things don't go so bad in the calculation. By the way, did we see in terms of the pH what we expected to see? The pH of acetic acid by itself without the common ion is 2.72. With the presence of the common ion in the solution, we would expect, based on Le Chatelier's principle, it to shift to the left, which means we should end up with less H plus than we had with the acetic acid and a higher pH, which we did at 4.92. So again, that's what we're talking about in terms of it's suppressing the weak acid. It's still able to break apart, still able to produce some H plus, but it will not produce as much H plus as the acid by itself. And thus we see a higher pH. Still an acidic pH, but higher than it would be if that common ion was not present. Any questions on that there? Well, in problems that usually involve the common ion effect, and we usually get starting concentrations that are relatively high, we could actually approach these problems in a slightly different way. And we could use actually an equation to solve for the pH rather than, say, an ice table. So if you do a little rearranging of some Kas and some pH type things, you get the Henderson-Hasselbalch equation here, which is really used in common ion problems, But really common ion problems, as we will talk about shortly, are buffers. So this is really our equation here that we typically use in a buffer situation because a buffer is a common ion situation. The pH here is equal to the pKa plus the log of the conjugate base over the acid. Now, to calculate the pKa is equal to negative the log of the Ka value. So we can use this equation in a buffer situation or really a common ion situation, and you do not need to use the ice table. You could just actually go right into the equation and get or the formula and get it. Now, most of the time when you are solving problems, I would say probably 9 times out of 10, they're going to ask you for what is the pH of that solution, which means, in my opinion, you could use the Henderson-Hasselbalch equation for any situation. It could be used for an acidic situation, neutral situation, basic situation. Sometimes people will use a version of the Henderson-Hasselbalch equation for basic conditions, where just like when we talked about pH, we also could solve for not pH, but POH. Yeah, so there is sort of a POH version of the Henderson-Hasselbalch equation, which is equal to the pKb for base, not acid, plus the log, and this is also flipped around, the acid over the base. Yeah. So those are also flipped around. I guess I should say my acid over the base there. Clean that up a little bit. To calculate the pKb, by the way, it is minus the log of the Kb value. Yeah. So why would you want to use that one? Frankly, I don't know why you would want to use that one, because in most cases you want the pH anyways. So this one I would be the one I would recommend using in all cases, but you can use the POH one if you like in a basic situation. Sometimes people will do that with basic buffers and kind of use that equation and then subtract 14 at the end. So you might as well just get the pH right off the bat. But there is a really nice relationship, by the way, between the pKa and the pKb value. Just like the pH and the POH equal 14, so does these guys here. So if you happen to have the pKa value, but you need a pKb or vice versa, you can subtract 14 from it and get the other value that you need. So that's a good relationship. Again, sometimes maybe you can only find the Kb value, so you can calculate the pKb and then subtract 14 and have the pKa. So, that's a nice relationship there. So my opinion would be to always roll with this one, because that's probably what you're looking for. And again, it doesn't matter if it's acidic, basic, or neutral conditions, it all should work. But again, you may sometimes see the other one written. So any questions on that there? So if we go back to the problem there that we just did, which was we had a 0.2 molar acetic acid along with a 0.3 molar sodium acetate. And we had a Ka value there of 1.8 times 10 to the minus 5. First off, the first thing you need to do is recognize that these two things are related to each other. Yes, they're essentially related to each other by the classic definition of Bronsted-Lowry, right? 1H plus difference between them. Then that's all you need to see. You could go right into your pH is equal to the pKa plus the log of the base over the acid, right, on this one. So base on top over acid. And in this case, we do need to calculate the pKa value, which would be minus the log of 1.8 times 10 to the minus 5. That's going to be a 4.74. And that means that the pH here would be 4.74 plus the log of our base. Which one's our base? What's the name of this guy? That's acetic acid, which means that's probably not our base, right? So the acetate there is its conjugate base. So that guy would go up on top and the acid would go on the bottom, right? So this is, again, a weak acid. and its conjugate base, which is essentially, as we'll talk about in 2 seconds, a buffer, pretty much. All right, so if we do that there, that's a 0.3 divided by 0.2, take a little log action of it, and then add a 4.74 to it. Dare I say I get a 4.92 without the use of an ice table. So you get the same answer there without having to do the ice table. With that being said, though, cautionary note, people want to use this equation in every single calculation known to man. And if you don't want a lot of X's on your paper, you should not do that. So this is only specifically for a common ion type situation, which is essentially a buffer situation. If it is not a buffer situation or really a common ion situation, you should not touch that equation with a 10-foot pole if you want to get the right answer. Yeah. So that is also speaking of more mistakes that people make, they just roll that equation on everything because, like, I learned it, I should just use it. And it very much happens anytime people get 2 numbers. Like, I got 2 numbers, got that equation, needs 2 numbers, I'm going in it. So very much should only be used in a buffer or common ion situation. By the way, this also shows you that if you don't want to use that equation, not sure you should use that equation, you could always roll with an ice table. So you could always use the ice table and not use the Henderson-Hasselbalch equation, and you should get the same answer. If you could recognize it, though, as a common ion or buffer situation, it can save you some time by just going into this equation, but you could always use the ice table for any situation. As you saw there, and as we did a few slides back there, right, we had the exact same answer, right? 4.92, 4.92. So I personally, again, would recommend, and just a recommendation, that if you do recognize it as a common ion or buffer type problem, which is basically the same thing, I would use the equation. Because most people, when they do that ice table, once again, forget to do the initial on the right-hand side and get the wrong answer. So just keep that in mind. Any questions on that there? Okay. So why don't we try this one here? What is the pH of a solution that contains 0.3 molar, I'm going to go with formic acid, and 0.52 molar potassium formate? Ka of formic acid, 1.7 times 10 to the minus 4. Let's take a look. We have formic acid here. And we have a little potassium formate here. And these two guys are related to each other, right? That is a weak acid, as we see a Ka value for it right there. This is also its conjugate base, right? This is really a salt. Out of these two, this guy here is going to break apart into ions. It is not going to stay together in solution. Out of the two, this is the only thing that would set up an equilibrium, as it's a weak acid in a solution. So basically, if we were going to take an ice table approach here, it would look something like this, with this guy breaking apart, just like a normal sort of weak acid problem. We initially did it here. We have 0.3. We have 0. And remember that if we take the ice table approach, we do have some formate in this case, which is the common ion here, right, between these two. And that is going to be 0.52 molar. So again, really important if you did that, that you do have a value there, and it's not 0, minus X, plus X, plus X. And at equilibrium, 0.3 minus X, X, and X. Now, if you took this approach just like normal, you would go into the Ka and solve for X. X in this case would equal your H plus concentration, and then allow you really to get to the pH. Now, you don't have to do any of that because, again, hopefully you can recognize that these two guys are related to each other. And this is, again, a common ion, really a buffer situation here, which means we could go right into our David Hasselhoff equation or Henderson-Hasselbalch equation, whichever they call it, these look here. And in this case, we could just calculate our pKa value, which would be minus the log of 1.7 times 10 to the minus 4. And we got here then 1.7 to the minus 4. A little 377 for our pKa. Going into our pH would equal 3.77 plus the log. Once again, our salt here is going to be our base, which goes up on top. And obviously here, this is our acid, which should go on the bottom. And we do want to divide first before we take the log. And we'll do a 3.77, a little 401 action here. Yeah. Once again, that should be the same pH if you follow through the ice table approach. Yeah. Any questions on that one? Yeah.
So on the test, if you found the pH using the ice table method for a problem like this, that would be okay?
That's perfectly fine. Yeah. So like I said, if you never want to use the Anderson-Osbach equation, you could always just continue to roll through the ice table. Should give you the same answer. Yeah. It just, again, may save you some time in certain situations. Other questions? Okay. All right, so we've been sort of dancing around the idea of common ion and really what we really call common ions in normal situations, and that is it is a buffer solution. So a common ion is, actually a buffer, or I guess the other way to say that is a buffer is really a common ion sort of situation that's occurring. So a buffer is made up of really one of two combinations. It is made up basically of a weak acid and its conjugate base, and sometimes is oftentimes referred to as the salt of its conjugate base, which just frankly means it's got like a sodium and potassium just hanging out doing nothing, basically, to make it an ionic compound. Or you can have a buffer that is made up of a weak base and the salt of its conjugate acid. So what is the relationship between those two things? It is what I was just talking about, is the Bronsted-Lowry definition. It should only be 1H plus difference between those two things. And they do have to be weak. You cannot have a buffer. You cannot have a buffer that's made up of a strong acid or strong base. Now, you cannot have a buffer and go, this is my buffer solution. It's been made up of a strong acid or strong base, because it cannot be. Now, not to overcomplicate it so far, but you can actually make a buffer from a strong acid and a reaction with it, but the acid is completely gone at that point when it's all said and done, and you're left with a buffer, but the buffer itself cannot be a strong acid or a strong base. The reason a buffer works, and as we'll talk about how a buffer works here in just a second, is that both of those things has to be present in the solution to begin with. So in the solution, when you throw your beaker down carefully and not break it, you need to have a weak acid, for example, in that solution, along with its conjugate base, or you need to have a beaker that has floating around in there a weak base and its conjugate acid. So once again, it is not a buffer if both of those things aren't swimming around to begin with, basically. Now, the reason why you cannot have a buffer made up of a strong acid or strong base is only a weak acid or weak base will set up an equilibrium. So for example, if I had everybody's favorite buffer example, which is acetic acid and sodium acetate. When you dump acetic acid and sodium acetate in there, that acetic acid is going to set up this equilibrium. Arrows and all, not really, but we'll pretend there's arrows inside the beaker. It's going to set up this equilibrium. So when you put the acetic acid in, that acetic acid will set up this equilibrium here. And that means that you at this point have a weak acid and its conjugate base in this buffer to start with. You help out the concentration of the conjugate base by adding in there with it some sodium acetate, right? Which is technically its conjugate base, because this is going to be a source of sodium, which is not important, but it is a source of more acetate. So by you adding the sodium acetate in there, what you have just done is you built up in your buffer a pretty good concentration of an acid sitting in there, and now a pretty good concentration of the conjugate base sitting in there. So essential to how a buffer works is it has both of those things present in the solution before you do anything to it. And the reason why a strong acid or a strong base won't do that, let's just say you wanted to make a buffer out of HCl, right? We know HCl will completely break apart into H plus and Cl minus, which means if you decide, hey, I want to make a buffer with HCl and sodium chloride, which is like a acid conjugate base situation, what you will have floating around that solution is H plus, Cl minus, and some sodium ions floating around, right? You will not have any of that HCl solution there because it's completely broke apart. So that is why a strong acid or strong base cannot be a buffer, because there's no way to keep the acid part in the solution and the base part in the solution at the same time. So only a weak acid can set up that equilibrium, which will keep everybody that you need in that solution actually in the solution. Any questions on that there? So what is a buffer? Most people have a wrong idea about the definition of a buffer. Most people will say it's a neutral solution, which is not correct in all situations. You could have a buffer that is neutral. You could have a buffer that's acidic. You could have a buffer that's basic. You could frankly make a buffer at any pH you choose along the pH scale. But what a buffer is a solution that has a specific pH. And even if you add more acid to it or more base to it, will be able to basically maintain that same pH. So for example, if you take the acetic acid sodium acetate buffer and you make it, most of the time you'll be somewhere around 4.74 in terms of its pH. And if you added acid to that buffer at 4.74, the pH will go down maybe a little bit. Maybe it drops to 4.6 something, but it will not drop like from 4.74 all the way down to like 1 or 2. You won't see a giant jump in pH. You will actually see some change in it when you add acid or base, but you won't see a really giant jump in the pH. Same thing if you had that 4.74 buffer and you added some base to it, like some sodium hydroxide, you will see the pH go up a little bit. Maybe it goes up to like 4.8-ish or something like that, but it will not go up from like 4.74 to like a pH of 10 or something like that by adding that base. So it's able to maintain whatever pH it's at by working as a buffer because of these two things attached, or that's in that solution. Any questions on that? So let's talk about how that actually works. So let's start with how it works when we do not have an actual buffer. So let's just use water, which is not a buffer. So we're going to take water, which is not a buffer, and we're going to add to water my hydrochloric acid, which is a strong acid. So when I dump some hydrochloric acid into my wonderfully drawn beaker of water here, that is essentially going to add H plus and Cl minus into my beaker, right? Because it's going to 100% break apart into H plus and Cl minus, which means when I do that, I just made a lot of H plus here and a lot of Cl minus. In terms of the pH, what's most important, it is the amount of H plus that I just made, right? I just made a ton of H plus, which means my pH, which is based off of the amount of H plus that's in that solution, my concentration of H plus just went up, which means my pH is going to go way down. So maybe you have some water that's 7-ish, maybe you got some good water in there, and you add some HCl to it, you will see maybe the pH go from 7 down to like 2, a pretty big jump, or 1, depending on how much you put in there. You'll see a really, really big jump in the pH because what you just did by adding the HCl to the water, which is not a buffer, can't really handle it, is you just basically dumped a bunch of H plus in there really quickly. And that's going to create a big jump in the H plus concentration, and you're going to see a very big change in the pH. Now, if I added, say, sodium hydroxide here to water, which again is not a buffer either, and that will break apart into Na plus and OH minus in that water. So the same idea here, if I had my beaker of water and I throw my sodium hydroxide in there, it's basically a source of these two ions here. What's going to happen in that solution is we're going to get a bunch of OH minuses floating around freely and some sodium ions floating around. Not really important because we know sodium is a neutral salt, right? So not going to do anything to the pH. But what I do have right now is a whole bunch of OH minuses, right? And because we know from talking about KW that if my concentration of OH minus increases, what happens to my H plus concentration? It goes down, right? Opposite, which means big jump in OH, big drop in H plus, which means my pH is going to go which way? pH is going to go way up, yeah? So in this case, if you added this sodium hydroxide to water, which is not a buffer, you're going to introduce into that water a bunch of OH minus concentration or ions really quickly. You're going to see the H plus concentration bottom out, and you're going to see a pH basically jump. So maybe it goes again from 7, maybe up to 13 or 12, depending on how much you sort of added in there. So that's what happens when we add like a strong acid or strong base to a non-buffer solution. Any questions? So what happens when we add it to a buffer? Dare I use the classic example? I don't know. So let's say we had a, let's just say we had a, use it, we'll use hydrofluoric acid, which is a weak acid, and a little sodium fluoride. I don't feel like writing acetic acid tonight, so we'll do this guy. All right, so first off, let's say this is like a buffer, maybe. HF is what type of acid? It is a weak acid, right? And this would be his conjugate base. This would really be the salt of his conjugate base because there's a sodium there. The actual buffer part, though, is which thing, the sodium or the fluoride? It is the fluoride, right? That is really the conjugate base, right, to our HF. Again, the Bronsted-Lowry definition of just one H plus difference, right, between those two. So when we have our buffer here, we have really, if you want to think about it, we have an acid part to our buffer, right? And this would be really our base part, right, to our buffer. Now, if we have a beaker of this, we would have some HF floating around. We would have our H plus and our F minus floating around in the solution. And once again, we have our acid part here and our base part here of our buffer, and pretty good concentration if we made it like this in this imaginary buffer. Now, if we were to take our hydrochloric acid, just like we did when we added it to water, and I dump my hydrochloric acid into here, this is going to be H plus and Cl minus, right? And what's going to happen is these guys are going to go in, and we have HCl, which is an acid, which means will the acid react with the acid part of the buffer or the base part of the buffer? They're called acid, what type of reactions? Acid base reactions. Yes, you never heard of an acid-acid reaction, right? Or a base-base, right? So they're called acid-base reactions, which means if I dump hydrochloric acid into my buffer, it is going to actually go find my base to react with in this case, right? And in this case, we'll leave the sodium on there if you like. And it's basically going to do a double displacement reaction, right? Positive, negative, positive, negative. Going to do a little switching of partners here. These guys are going to switch partners. And we will produce a little HF and a little NaCl. Wow. So what we see here that was produced when we add the strong acid to our buffer is we produced some more of HF, which was the acid part of our buffer. And by the way, that always happens. You actually use part of your buffer in the reaction, but then you always produce the other half of your buffer. So if you're not sure what goes on the other side of the arrow, it's the other half of the buffer goes on the other side of the arrow. We also produce this guy here. And obviously, if we produce HF, which was part of the buffer to begin with, not going to probably affect the pH. We got this guy, which is a sodium chloride salt. Yeah. What type of salt is that? It is a neutral salt, right? It is a group 1 sodium, which means nothing's going to happen. It's Cl minus from HCl, which is a strong acid, which means it's not going to happen. It's going to be a neutral salt. So that's probably not going to screw up the pH. Yeah. But it is actually what we don't see there that we did see when we added the HCl to water. What do we not see in the bottom equation that we did see in the top equation when we added the HCl? Top equation, we made a lot of H plus. Over here, did we make any H plus? We did not make any free H plus. And it is the free H plus that screws up the pH, frankly, yeah? That's what the pH equation is, minus the log of the free H plus. So in this case, we actually did not produce any more free H plus. So no free H plus was produced, which means if I didn't produce any more free H plus, that amount of H plus that was there to begin with pretty much stays relatively constant. So the amount of H plus stays relatively constant. Really, the concentration of H plus stays relatively constant. And if that happens, the pH stays relatively constant as well. I say relatively constant because if you stick a pH meter in there, like you're going to do after the exam on Tuesday, you will see the pH move, but it will not jump really big. So again, in this situation, if you added it, maybe it goes down a few, and it should move in the acidic direction, right? Because you're adding acid, so the pH should go down a little. But again, you will not see a giant jump in pH because unlike what happened here when we added it to water, we generated a lot of H plus. Here, we pretty much have the same amount of H plus we started with, and that's how it's able to maintain basically the pH when we add a strong acid to it. Any questions on that there? So what happens when we add a strong base to this buffer? So we'll take a look at that here. So I'll just clear this out here. So let's say we had our same buffer here. We got our same little beaker. We got our HF that's going to set up an equilibrium. Arrows and all. And F minus. And once again, we have our acid part of our buffer. We have our base part of our buffer. And now we're going to take sodium hydroxide and add it to our buffer. So sodium hydroxide, once again, is a source of these two ions, which are going to go for a swim here. And when they do, since sodium hydroxide is a base, will it react with the acid part of the buffer or the base part? It will react with the acid part. So it's going to do just a regular old acid-base reaction here. So we're going to get a nice regular acid-base reaction. Also a double displacement reaction as well, where we will make a salt and water. So we'll make a little sodium fluoride. And we will also make some H2O here in this particular case. Again, switching partners basically to get us there. Now, when we look at this reaction with the buffer, we see the same thing. Although we used some of the HF, we actually made, again, the other part of the buffer in this case, the sodium fluoride. Not going to mess up the pH. We also made water, which will not mess up the pH either. And much like what we saw when we added the acid, it is something we do not see here that we did see when we added the base here to water. When we added the base to water, we produced a lot of hydroxide really quickly. Here, when we added that same base to our buffer, we did not create, put it this way, no free OH minus was produced. And what that means is the concentration of OH minus will stay relatively constant. And because the concentration of OH minus and H plus are tied together, as one goes up, the other goes down, that would also mean, once again, that the concentration of H plus will stay relatively constant, and thus the pH will stay relatively constant as well. So when you add a strong base or a base to a buffer, what happens is the acid part will basically tie up the OH minus and we will produce some water. And that OH minus that normally would be freely floating in that solution essentially gets tied up in water and no longer free. And the result of that is it keeps our H plus concentration constant. And the same sort of thing happens when we added our acid. When we add our acid to the buffer solution, the H plus and the base part of the buffer will come together to make more HF and also prevent basically that free H plus from entering the solution. And that is, again, essentially why a buffer has to have both of those things in the solution to begin with. It's got to have an acid part and a base part so that when you add either acid or base to your buffer, it's able to basically prevent the formation of free H plus or free OH minus. And by doing so, that's going to prevent big swings in the H plus concentration in your solution. And that's going to keep your pH from going crazy. Once again, it will move in both directions. So for example, with the base, if we added it to our buffer, we'll see it go up a little bit. By the way, when you make a buffer in a real life situation, even though you calculate how much you need of things to make a buffer, you'll never be able to measure it out correctly. You'll never get the exact pH that you need. And because buffers can resist big changes in pH, you could actually use a strong acid or a strong base to dial in your buffer to the exact pH you want. Literally like almost drop by drop. You can see the pH just move very slowly and you could dial it in exactly to the pH that you need by using an acid or base, because you don't have to worry about adding the acid or base and the pH go in really big jumps. It'll actually move very, very slowly and you can really lock it into the pH that you need. And that's how you actually adjust the buffer out when you make it in a real life situation, because it will never be exactly what you calculated in terms of the pH in an actual situation. Any questions on buffer there, how it works? So essentially, a couple other things here when we're talking about our buffer. You can think of a buffer like this, a lot of times when we make a buffer, we oftentimes would like to keep kind of the concentration of our acid part and our base part of our buffer. So our acid part, which is sometimes just abbreviated as HA, and our base part of our buffer, which is abbreviated A minus. And a lot of times we like to sort of start with it about equal concentrations of each other. And when we add acid to our buffer, we will use up some of the base part, but then again make some of the acid part. So dramatically drawn here, we will see the acid part of our buffer dramatically go up here. And we will see the base part of our buffer go down. And same thing happens when we add a base to a buffer. It will react with the acid part of the buffer and use some of it up, but it will produce the base part of the buffer. So once again, here we will see the base part of the buffer go up. And our acid part of the buffer go down. There is something known as buffer capacity, which means, frankly, when you make a buffer, you have to actually think about certain things if you want to make a buffer that works well, that actually will function as a buffer. You have to think about the concentration of your buffer that you want to make in relationship to the concentration of the acid or base you're going to be adding. Because if you make those things in the wrong concentration, like your buffer is not a very big concentration, but you hypothetically go grab the wrong bottle of HCl off the shelf and dump in there like the 18 molar versus the 0.1 molar, there might be a slight difference. You'll blow right through your buffer. It won't be able to handle it. So when you make a buffer, you have to kind of make it at the right concentration to sort of handle the acid or base that you're doing there. By the way, what would happen in this situation if I just keep adding acid? Let's say I had this buffer here and, I was not paying attention. Not that anybody would do that. And if I just keep adding my acid, maybe I'm doing a titration where I'm just adding more acid and adding more acid. I ignore all the color changes in the indicator and keep adding acid. What's going to happen eventually here to my base part? I'm just going to continue to what? Chew it up, right? Every time I add acid, I'm just going to chew more and more in my base part of the buffer. I'm going to make more and more of this part of the buffer. Eventually, I will run out a buffer that has the base part, right? And if I continue to add my acid, what am I now doing? I'm just basically adding H plus, right? And it's at that point, right? You will see a small or big jump in the pH. Big jump in the pH, yeah. Which is what happens actually in titrations. When you blow through a buffer part of your titration, you get a big jump in the pH. We'll talk about it when we get to titrations, but you will recognize that as the famous saying when people do titrations, I just added one drop and it went super dark pink, right? How many people said that? I don't know. I just added one drop. The thing went really dark pink. It went really dark pink because you blew right through your buffer and the pH jumped very drastically. And that made your indicator, as we talked about on the last class, works on a pH range. So your pH range just jumped really far. And you went from like no color to super dark fuchsia pink, which I love. I like that color when I do titrations. But that's really why we'll talk really why that happens and we'll get there. But that's essentially sort of what's happening in that case. So there is a thing known as buffer capacity. You can blow through a buffer if you add the wrong amount that the buffer can't handle when you're doing it. How do I know how to pick something to make a buffer at? Well, the buffer pretty much equation that we use for buffers, because it is a common ion effect, is the Henderson-Hasselbalch equation. So it is a common ion effect because it is a weak acid and its conjugate base, right? Which is basically a common ion, or a weak base and its conjugate acid, which is a common ion. So if I were to make a buffer where the concentration of the acid and base were pretty much the same, that would mean that this number would equal what? If B and A are the same number, it equals 1, which the log of 1 equals 0, right? That means when you go to choose what you want to make your buffer out of, you would want to look for a weak acid or a weak base that has a pKa value of typically plus or minus 1 of the pH you want to make your buffer for. So for example, if I wanted to make a buffer in the range of 4.6 or 4.7, acetic acid is a very good choice, and sodium acetate, because acetic acid's pKa value, which you will memorize at this time because it's the most common example used in buffers, and that number pops up like every 2 seconds, is about 4.74. So that's right there in the range of like 4.6, 4.7. That would be a really great choice. A really crappy choice to choose to make a buffer at a pH of 4.7 is something like ammonium chloride. which is based off of ammonia, which has a pKa value of 9.25. That's a long journey to get down to 4. So it's not going to be a really good choice to choose to make a buffer out of. But that would be a really good choice to make a buffer in the pH range of 9. Yeah. So you would go to a Ka table or Kb table, and you would want to calculate the pKa values of everybody you're looking for. And usually within ±1, or really as close as you could get to the pH you're trying to make your buffer at. You want to try to find a pKa value that's as close as you can. The further away it is, a lot more stuff you got to kind of put in there and make it, and it's not as good. So the closest you could get to that sort of desired pH, you want to look for a pKa value similar to that. Any questions on that there? Buffers. Like it. Love it.